In this video, we're here to help you understand why the wave equation often feels challenging to grasp. Even many physics educators, despite teaching it, might struggle to convey the intuitive understanding of waves and their behavior. Here, we'll not only explain the wave equation, but also give you a clear sense of what waves are, how this equation describes their behavior, and most importantly, what actually causes waves. What to expect. Foundation. We'll start by breaking down the basics of waves. Cause and effect, then we'll explore the origins and effects of waves. Derivation for advanced learners. Finally, for those interested, we'll derive the wave equation from Maxwell's equations in the context of light and electromagnetic waves. The wave equation. To make it simpler, we'll rewrite the wave equation from scratch. This general equation describes how various types of waves propagate. While it's typically written with partial derivatives, we'll use a simpler notation to represent the wave function as u, indicating displacement. Key components: left side, time component, the second order time derivative, which represents acceleration over time. Right side, spatial component, the wave speed squared times the second order spatial derivative, indicating the wave's curvature change over distance. What is a wave? A wave is essentially a disturbance traveling through a medium, disrupting the previous calm state. Example: imagine a still pond surrounded by trees. Throwing a pebble into the water causes ripples to spread out, disrupting the water and creating waves. This disturbance in the pond is the wave, moving across space and over time. The spatial curvature describes the ripple's behavior as it spreads, governed by the wave speed, while the time component shows how the wave propagates as time progresses. Core insights of the wave equation. The wave equation demonstrates that when a disturbance happens in a medium, what we call a wave, energy moves through, causing a disruption that spreads out. Here, u, displacement, captures the effect on molecules in the medium, such as water molecules in the pond. Waves are not physical objects, they're energy transfers across a medium. Understanding the cause and effect in waves. We may wonder about the cause and effect in the wave equation. Does curvature cause acceleration, or is it the other way around? To explain, let's consider Newton's second law, force equals mass times acceleration, where force generates acceleration. In the wave equation, there's no explicit force term, but we could add an external force F to represent the initial disturbance. Example: in the pond, this force could be the pebble hitting the water, initiating the ripple effect. By adding F to the equation, we get a clearer sense of cause and effect in waves. Unlike individual objects in Newton's law, waves are disturbances that affect entire regions across space and time. External forces like wind or seismic activity, for example, ocean waves or tsunamis, are examples of forces that can initiate waves in a medium. Deriving the wave equation from Maxwell's equations context, we'll explore Maxwell's equations in free space where no charges or currents exist. Faraday's law. We start with Faraday's law, which states that a changing magnetic field induces an electric field. By taking the curl of both sides and applying vector calculus, we transform expressions to reveal the wave equation for electromagnetic waves. In this form, the speed of propagation is determined by the permittivity and permeability of free space. Understanding electromagnetic waves. Electromagnetic waves are disturbances in the electric and magnetic fields propagating at the speed of light. In these waves, the electric and magnetic fields oscillate perpendicularly to each other and the direction of wave travel, described using the right-hand rule. Light waves consist of these oscillating fields and do not require a medium to propagate. Summary. Waves are energy transfers that travel through a medium or space, with electromagnetic waves being a specific type involving oscillating electric and magnetic fields. Understanding the wave equation, cause and effect, and derivations from Maxwell's equations provides insight into the nature of waves in both physical and electromagnetic contexts.